So the story begins in 1935 when Einstein wrote a paper with Rosen where the first time Einstein-Rosen bridges appear. And these are bridges that connect two seemingly unconnectable pieces of space-time.
ER, Einstein and Rosen, they pointed out that solutions to general relativity allowed for two black holes, which are connected, but with a kind of bridge, what we call a wormhole. But that wormhole has the property of being non-traversable.
Wormhole is a very unstable passage. It opens and it closes and it gets chaotic and it gets destroyed very fast.
So Einstein, when he proposed the wormhole, he was very frustrated because you couldn't actually go through a wormhole, and he was able to realize that himself. And so what good is a wormhole if you can't put anything through it? And it turns out that that's because he wasn't putting in the quantum physics.
Another interesting feature of the Kerr metric is its description of the singularity at the center of the black hole. First of all, some of you might be familiar with the idea that at the center of a black hole, there's a region of what we suspect is infinite density. Basically, mass is packed so tightly into such a small space that the density, basically mass divided by volume, is infinite. At these singularities, our mathematics breaks and our minds blow up. But luckily, we don't know yet what happens at the center of a black hole because we don't have any way of getting information from the center of the black hole. Still, it's worth thinking about. And interestingly, for a stationary black hole, the singularity is thought to be a very tiny infinitesimal point. Whereas the Kerr metric actually tells us that for a rotating black hole, the singularity is not a point, but rather a ring. A very thin, very narrow ring around the rotation axis.
1935, same year, another paper, the EPR paper, which is Einstein, Rosen, Podolsky.
EPR is about quantum entanglement and what Einstein called spooky action at a distance, something he was not happy with.
Entanglement is this property that subatomic particles, they are partners. Even if you take them apart and take them at the other edge of the universe, they hold information that if you measure the one, you know what the other will be. So entanglement is a strong correlation.
Einstein didn't like quantum mechanics, and this made it very challenging for him to understand how to reconcile quantum physics and gravitational physics. Physicists want to understand as much as they can about how the universe works, so it has been a challenge which has occupied many scientists over decades to understand better how quantum physics and general relativity fit together into a coherent picture.
Einstein's dream was to figure out how to connect them.
Those two papers, there was no reason to think at the time or for decades afterward that they had anything to do with one another apart from there being some authors in common.
And then comes 2013, Maldacena and Lenny Susskind. They say ER equals EPR. They are the same. This is very daring.
Wormholes and entanglement are the same thing. That was totally unexpected. One of them has to do with general relativity. One of them has to do with quantum mechanics. Didn't seem like they had anything to do with each other.
A lot of times in physics, you can have two different descriptions of the same thing, but it's just sort of a remapping of the same physics. And we call that a duality.
The basic idea was that when you have quantum entanglement between two black holes, necessarily there will be a wormhole connecting them.
It's like saying gravity equals quantum mechanics, if we want to say it in a simplified way. So there we have a picture of quantum gravity.
We have this dictionary that relates gravitational phenomena to ordinary quantum physics.
You can tackle the same physics from these two different angles, and that's the most concrete paths forward we have in building a full theory of quantum gravity.
The physics of the black holes, we think is physics of quantum gravity, but we cannot send an experiment in a black hole and validate that.
So instead, we can ask, can there be quantum systems whose dual description looks like wormholes? I think it might have actually been during a talk by Juan Maldacena about dr equals EPR that I started to wonder to myself, could traversable wormholes exist, right? And people thought it was fascinating as an exotic configuration of space-time, but I think many people probably suspected that it couldn't work. So we saw that it could.
One of the magical things about quantum mechanics is you can actually have negative energy, and this allows you to do things that you would have thought otherwise were impossible.
What Daniel Jaffrus showed was that if you introduce what's known as a negative energy shock wave, you can support your wormhole and get something from one end and have it come out the other.
Now I'm an experimentalist, so I look at that and I do, all right, what can I do about that?
We were thinking, we have the ability to do things in quantum in the laboratory. We're physicists. So could we imagine actually doing something with wormholes? It almost occurred to us immediately that we should be using the best quantum system that we know how to manipulate. And what is that? It's a quantum computer.
Quantum computers speak a different language than the ordinary language of bits. A bit, you look at it, okay, it's a 0 or 1, that's it. The correlations among qubits are richer and a lot more interesting than correlations among bits. It's this language of quantum entanglement. And so there's a world out there, this extravagant quantum world, which we just haven't been able to explore.
I've worked on a few projects at Google Quantum and got to know the device a bit. And the Google device is the best quantum computer that is around. All the magic happens in this little chip. You have the actual qubits as these superconducting pieces of aluminum, and that's where the entanglement happens. We had the access to the Google quantum computer. I came over with Maria and Daniel and Joe, and we were like, we have a proposal to try to, observe a wormhole on the quantum computer.
And to put the proposal together, it was obvious these are the people.
In physics, you have to have the courage of your own convictions, and you say, well, maybe it won't work the way that I thought, but we'll learn something by trying. And that's really the attitude we had going into this. I don't think we really thought it was going to work, but we thought we would learn a lot by seeing how far you could get.
They didn't say, you're crazy, let's do something else. They said, okay, you're crazy, let's do it.
You can use the holographic duality to create the quantum version of the system. We look instead at this set of entangled qubits, and we evolve it in a way that has exactly the same physics as the gravitational wormhole. And so on the quantum computer, we can directly send a qubit from one side of the wormhole and watch it come out the other. If you take the physical system that theoretical physicists say, this is a wormhole, and you work out pencil and paper, so how good of a quantum computer do I need? You get an answer that's like a quantum computer 10 years from now. It looks hopeless.
But we thought, let's try.
All right.
So we are here in our GQ2 lab, and then the controlled signals actually are produced in these racks sitting next to the cryostat.
When you try to just run a wormhole as the theorists have prepared it on a quantum computer, you find that you need to implement this very large system.
So that's big. That's a big, fat problem. I cannot put it on an experiment.
And so what we have to do is we have to do what physicists call coarse graining. So you want to preserve certain features, in this case gravitational features, while throwing away all the unnecessary components. We knew we needed to go to a smaller system size, and so we were kind of banging our head against it for a year or something. And then finally you come up with a weird idea that might work. The idea of rewriting it as a neural network is something that's kind of out there, and that's like it's a weird idea because you usually don't think of physical wormholes as neural networks. The wormhole itself that has like these many parameters that we treat as neural network weights. We then have a data set that we're going to train on, which is the dynamics that we want to observe that correspond to a wormhole. So it sounds like a generic machine learning problem now, and we can just like plug it straight into the machine learning toolbox. I proposed the idea and tried it out. The original system has 210 terms. The machine learning managed to keep all this intact while making a much smaller system.
It's still baby enough that it fits on the crib.
That was the kind of first moment where like, it might be possible, you know? this whole wormhole thing we've been talking about for 2 years, like maybe we can actually do it. At probably like 2 in the morning, I was running these quantum circuits. We're looking for a peak. That's the qubit making it through the wormhole. I'm watching the data as it comes out. There's a little bit of a noisy peak. At first, I was like, this is probably just noise artifact. But as the data kept coming and the peak kept getting clearer, it was like, this is a wormhole. I think I just saw one. And so I was immediately like sending it off to Maria and the others. Like, I think we have a wormhole, guys.
He said, it's there. I said, no kidding, he's there. It was nuts. It was nuts.
What happens is
The qubits of the Google quantum computer are making a little bit of extra space, and that's our wormhole.
a pulse of negative energy falls into the wormhole.
Now the wormhole becomes traversable. It opens.
You put a qubit through one side of the wormhole.
The qubit is now in the interior of this wormhole.
That information will actually spread over the entire quantum system. This spread of quantum information,
It becomes shared by many particles in the form of quantum entanglement. And then, rather remarkably,
it has to refocus as a single qubit. And then as the wormhole is closing, the qubit is exiting.
Completely empty space should have some real energy. It should have vacuum energy. In 1948, the Dutch physicist Hendrik Casimir came up with a brilliant scheme to detect this. He imagined two conducting plates brought so close together that only certain virtual photons could exist between the plates, in the same way that an organ pipe or a guitar string of a particular length only resonates with waves of certain frequencies. Any non-resonant virtual photon would be excluded, reducing the vacuum energy between the plates. However, on the outer surface of the plates, all frequencies of virtual photon are allowed. The higher vacuum energy outside compared to the inside of the plates should result in a pressure differential that pushes the plates together. The Casimir effect was only successfully measured in 1996 by Stephen Lamoureux at the University of Washington, based on the initial ideas of his student Dev Sen. When separated by less than a micrometer, conducting surfaces were found to be drawn together by a force that matched the predictions of quantum field theory. Now, while there are potentially other explanations for the observed force, this has been taken as strong evidence that vacuum energy is real.
Today I'm going to talk about human traversable wormholes. My talk will be based on two papers. The original construction from 2 years ago, which first proposed using Casimir energy to build traversable wormholes. And then the second part of my talk will be based on this recent paper, or how to embed those in the Randall-Sundrum model and make them humanly traversable. So what are the traversable wormholes? So this is a picture just of a wormhole. So we have two space regions which are connected by a handle. And we say that its wormhole is traversable if an observer can actually travel through the handle. And it is humanly traversable if a Homo sapiens can travel safely. And I would like to point out that safely means it's safe for both the Homo sapiens and the wormhole. Wormholes are actually quite fragile too, but in a different way. I will explain it in a bit. So in my talk, I would like to answer two questions. So do such objects exist in classical Einstein gravity in 4 dimensions without exotic matter? And again, in just in one slide, I will explain what I mean by exotic matter. And the answer is yes. And the second question is, can they be made humanly traversable with matter which is roughly consistent with the current observations? And the answer is yes. Although in my case, we did not include very stringent constraints, but at least the matter contact we're gonna talk about it makes sense. Okay, let me explain what I mean by not exotic matter. So these are the familiar Einstein equations where G Newton is just a constant, which is in our universe is this. And T mu is the stress energy tensor of matter. So the properties of the matter determine the properties of the space-time. And the traversable wormholes requires the so-called negative energy. And the physical reason for this is that the two sphere inside the wormhole, it first shrinks and then expands. And so various theorems in Einstein gravity prohibit this unless we have negative energy. And precisely, let me explain what I mean by this. So if we have a simply negative cosmological constant, in some sense it does lead to negative energy, but this is not what we actually want. What we want is the violation of the so-called average null energy condition. So it means that we take non-extendable null geodesic, integrate the corresponding null component of the stress energy tensor along this null geodesic. And so this is a neck, and for a traversable wormhole, this quantity here, it should be negative. And a neck is violated by the famous Casimir effect. So I should point out that all classical matter satisfies this requirement. So, but the Casimir effect, it's quantum, so it actually violates this. So let me remind you what Casimir effect is by an example. Suppose we have a massless fermion on a circle of length L, so just in 2 dimensions, and we can impose antiperiodic boundary conditions and compute the difference between the energy on the circle and energy in flat space-time. So this energy difference is actually UV finite, and it equals to this, it's negative, and it leads to the following non-null component of the stress energy tensor. So this is precisely what we want. And notice that this quantity is proportional to the Planck constant, so it's small, so it's a quantum effect. But I believe that it has been actually verified experimentally. So one maybe technical comment is that in our case, the space-time will be curved, but the Casimir effect can be generalized to this case as well. We just need to take into account the conformal anomaly. So this is again the picture of a wormhole, and indeed in this case, when we have a wormhole, we have one cycle which is not contractible, And this is very similar to the case with these fermions living on a cylinder, because they can go around this cycle. So when we introduce it, if we have matter, then it will produce a Casimir effect and produce negative energy. So this is the idea, to use this negative Casimir energy to construct the wormholes. But there is a problem, because we need a lot of matter, because not only we have to compensate for the Newton constant, but also we have to compensate for the Planck constant as well. And so one observation is this: we can actually use magnetically charged black holes for this purpose. So this was proposed in our paper with Juan and Fedor. Essentially, if we take magnetically charged black holes with charge Q, then it has been known for some time that free Dirac fermions in this background, they support two-dimensional fermionic modes. This is known as Kalin-Rubakov effect. It has been known since 80s, and it's valid not only for black holes, for monopoles as well. Perhaps I should clarify why are they two-dimensional. Let me just draw a picture. So this is, say, a two-sphere, and we have a magnetic flux coming in all directions. And roughly we have one fermionic mode per unit flux. So it means that this fermionic wave function is in fact localized on a scale of radius divided by the square root of Q. So if we go to the energy scales, to scales above this length, let's call this LB. Then we can essentially neglect the inner structure of this fermionic wave function, and we can just concentrate on its movement in the radial direction. So essentially they become effectively two-dimensional. So are there any questions on this point? So, okay, actually this equation, we should remember this because it will appear later in our discussion when I will discuss holographic matter. That the point is that below a certain energy scale, we can treat these modes as effectively two-dimensional, and they will have two black holes. Then they can propagate along the magnetic lines. This is actually even observed in the on Earth, because you know that there are polar lights, because the charged particles from the outer space travel along the magnetic lines of the Earth. So you can see them in the poles. And this is exactly the thing which can happen between two magnetically charged black holes. These massless modes will propagate along the magnetic lines. And this is why it's good for us, because it means that all these excitations, they won't just spread around in 4 dimensions, but will travel exactly along this effective 2-dimensional cylinder. But there is a problem with this, because if we assume that even if we have some dark sector with this dark U1 gauge field, it requires an enormous number of fermionic fields in order to make it macroscopic and Humelit reversible. So number of fermionic flavors should be 10 to the 52. So it's extremely unlikely that there will be a dark sector with this number of weakly interacting fermions. It means that one will have to tweak the coupling constant to be smaller than this number, because these fermions, they can travel in loops, and so the effective coupling constant is in fact multiplied by this, and it would be true even for gravity interactions. So such big number of fields would mean that they would strongly interact with gravity well below the TeV scale. So this is just does not make any sense. So then I guess one natural idea is that what we try to describe the matter holographically as well. So we say that we have a two-dimensional CFT described by 5-dimensional random syndrome. And the question is, what happens in this case? Do we still have these massless modes or not?
In Newtonian physics, around a compact mass, you can place an object in a circular orbit at any radius, and it will be stable. It doesn't matter how close you get. This is not the case according to general relativity. Here, there is an innermost stable circular orbit, with a radius known as r ISCO. Closer than this, and no orbits are stable, they all fall into the black hole. So when you're looking at a black hole that is feeding, the innermost edge of the accretion disk is at r ISCO. What's useful for our purposes is that r ISCO depends on the spin of the black hole. The faster it's spinning, the smaller r ISCO becomes, assuming it's spinning in the same direction as the matter in the accretion disk. The rotation enables particles to orbit closer to the black hole than they'd be able to for a non-spinning black hole. So you can kind of think of it as though the spin is supporting the particles against the relentless pull of gravity. Now, spin is normally discussed in terms of a dimensionless parameter that ranges from 0, no spin, to 1, maximum spin. Though I guess you could also have spins down to -1 if the black hole is spinning in the opposite direction from the accretion disk. Now, as spin increases, r ISCO decreases by a factor of 6, shrinking down to the size of the event horizon. And this sets what many scientists think is the maximum spin a black hole can have,